Okay. Hello, in this meeting, this 7. So we are going to focus on some general concepts on techniques for sure. Whatever we are going to cover now will be repeated with you in many other courses, but in more detail. So it will be a good starting point to understand the main concepts we are going to cover in this class today. Now, what is the digital media? What is human complete interaction? Okay, concepts interaction. This is what we will discuss at the end of this class. Okay. So the term digital media includes both the tools we use to create media such as text, images, audio, video, and also the idea of communicating and sharing through the internet and the web. Okay, so all about the tools that we will use in to create media, okay, from such as text, such as images, audio, video, okay, and the idea of communicating this media, okay, through the internet or through the web, okay, all this, it is called the digital media, okay. So the digital media includes all of this. Technologies have developed the production and distribution of digital media content as well as its consumption. Okay, so here the technologies have developed the production and the distribution of digital media content, okay, as well as its consumption. Whether in an educational or training context or in a work-based setting, the use of audio and video offers a richer and more interactive environment for educators or other presenters to express messages, okay? So we need some videos, we need some audios, okay? To keep the communications, okay, or the training or the educational context more interactive, okay, richer or okay for educators, okay. So most material on the web can be grabbed, copied, modified, but this is often illegal, okay. So you need to be aware of that. Privacy and copyright, okay, it is the intellectual property rights are indeed areas of great ethical and legal concern. Okay, so we have already seen the plagiarism, okay, so you need to refer the person or the text or the article or whatever, the website, where you find the idea, okay, and you copy it, okay. So this is some from an ethical, okay, concern, okay. So let's begin by representing the real world in digital form. So as you know, there are two major ways of representing information from the real world, okay, like temperature, speeds, whatever, okay, the information that you get, you need to represent this information. So we have two ways, okay, to represent this information: the analog representation and the digital representation. Okay, as you know, we live in an analog world with an infinite range of sounds, colors, touches, tastes, smells, okay, that we can perceive through our senses, okay. Everything that you can sense, that you can perceive, okay, it is an analog world, okay. You can listen to many range of sounds, you can see many colors, you can touch, okay, many information like heat, cold, etc. okay. You can taste, okay, you can smell also. So all this, okay, uh, includes or constitutes the analog world. In analog representations, the representation is equivalent of the real world aspect that we are trying to capture, okay? It is the same. We don't carry any modification or any modulation or whatever, anything. Okay, it is as it is. Okay, this is the temperature. Okay, this is the temperature. I will not change this temperature. Okay, for example, this is the speed. It is okay. So the temperature is an analog and can take on any value within a given range. And when the temperature is measured by a traditional mercury or alcoholic in glass thermometer, we have a continuous and analog representation. So this is the main feature of the analog representation. It is the continuous. Okay, it is a continuous. We don't have some discontinuity. Okay, we don't have some interruption in the values. Okay, taken by the information or by the temperature. Okay, so it is a continuous. You can see here. You can see how it is continuous. Okay, like that. Okay, so this is, for example, the time, and this is the temperature. Okay. So as you can see here, the temperature is a continuous, okay, has a continuous value. Okay, is it clear? Clear? Okay. Okay, I need your feedback. Huh? Okay, so this is about analog representation. Another way to measure temperature is by using a digital thermometer. Okay, now it is not the traditional one, it is another one, that it is the digital one, where a sensor is used to convert the temperature into an electrical voltage. Okay, so as you can see here from this figure, this is the digital, okay, thermometer. At this stage, the representation is an analog voltage, but an electronic circuit converts the analog voltage into digital representation as the numerical value of degrees Celsius or Fahrenheit. Okay, so this is the process how we can measure the temperature. There are some analog voltage. We will represent the analog voltage. Okay, and this electronic circuit will be converted into analog voltage from the analog voltage to a digital representation as a numerical value. So this means that the values are converted into discrete values. Okay, you can see here a new keyword, discrete, not continuous. Okay, it is a discrete values. A discrete value is something that can be counted, whereas the continuous data is measured. Okay, so when we measure something, it is an analog or it is a continuous data. But when we can count this value or the value of one information data, okay, it means that it is a discrete value. Okay, it is not continuous. So one example of a discrete quantity is the number of people in a room. So the number of people in a room can be counted. Okay, 1 person, 2 person, 3 person. We don't have 1.15%. Okay, 1.16, 1.17. Okay, we have only the whole numbers. Okay, so all this, the number of people is a discrete. Okay, is a discrete value, has discrete values. Okay, but the temperature, the speed of the wind, etc. are analog data or analog values. Okay, so they can be they are continuous. Okay, they have continuous data or values. Okay, so this is the difference between the analog representation and the digital representation. The analog data and the digital data. The digital data, okay, it means that we have discrete values. We don't have many values, okay, continuous values. We have discrete values that are countable, okay, but the for the analog data, so we will have continuous data that is measured and not countable. We cannot count the number of temperature, okay, we can just measure, okay. So this is the representation of two temperature plots on the same axis. One plot of a continuously varying temperature, and the other the corresponding series of discrete values that may come from a digital thermometer. Okay, so the black line here is the analog. Okay, the analog temperature, it is taken by the traditional thermometer, okay, but the blue one, it is discrete, okay, we have discrete values, okay, it is not continuous, so these values were taken by the digital thermometer, okay. So this is the difference between an analog data and the digital data. This is the digital, okay. It has discrete values, but the analog will have continuous values, okay. Is it clear right now? The difference between analog and digital data? Clear? Okay, Ahmed, Sadia, what else? Where are you? Okay, Faris, Lud. Ibrahim, Faye, okay. Okay, thank you. Okay. So let's move to this activity. So which items in the following list are fundamentally analog and which are fundamentally discrete? So the amount of heat from a file, is it a discrete or a continuous value? It is a discrete, digital, or an analog value? The amount of heat from a file, good, Ahmed, it is an analog, okay? We cannot count the number or the amount of heat, we can measure. Yeah, good. Okay, sorry, the energy of a star, the energy also is an analog, okay? We cannot count the energy, we can measure the energy, okay? Okay, the pressure of the atmosphere, the pressure, is it continuous and analog or discrete and digital? Good, Sadia, it is an analog. Ahmed, good. Okay, the price of petrol, the price of petrol, okay, the price of petrol is digital, is discrete. Every day we have one price, okay? We cannot have smoothly varying price of petrol, okay? Good. Okay, for the 5, the size of audience. The size of audience, is it analog or digital? Yeah, it is digital, it is discrete, okay? We can count the number of audience at a play, okay? And for the speed of a car, the speed of a car, yeah, good, Sadia, good. It is an analog, it is a continuous, okay? We can have whatever the speed, okay? From, sure, it is under 200, okay? But it can be, okay? Any values, okay? So this is an activity to evaluate your skills, okay? Your knowledge in comparison between analog and discrete data, okay? Move now to the representation. So the representations now play a central role in facilitating communication by establishing a relationship between some perceptible form or symbol, and associated meaning or content subject to some convention. Okay, so there are some symbols. We cannot write everything. We cannot. Okay, we can represent. Okay, represent, and it means that we can use some symbols, some contents. Okay, that will show. Okay, and it is subject to some convention that will show you to the meaning. Okay, to show you the meaning of the place, for example, or whatever. Okay, so look here, for example, crosses on churches, okay, or crescents on mosques, indicate places of worship, okay, and are intended to be seen. Okay, we will focus on the side, okay, on the side of a human, okay, to indicate that there are this place is designated for worship, for example, okay, or يعني it is the same for the for all for all people. Okay, it is seen. Okay, also the blips at pedestrian crossing, okay, indicate the light is green and are intended to be heard. Okay, so you can see the pedestrian, you can use this pedestrian once the light is green. Okay, so this is some convention. We use some convention. There are some convention and some symbols to use, and it will be associated to some meaning. Okay, the pedestrian is mean that you can use it. Okay, once the light is green. Okay, the crosses or the crescents, okay, on mosques, so you can use this place to pray to okay, so this is some symbols. So to be effective in communication, a representation must meet at least the following conditions. Okay, we need to be efficient, to be effective in communication. So we need some representation, some requirement on the representation. So the first is the form of the representation must be perceivable in some way. You need to make the form of the representation perceivable. Okay, by sight, by heard, okay, by I don't know, by touch, okay, by taste, whatever. Okay, so there are some symbol, okay, and these symbols are perceivable. Okay, and the relationship between form and content and meaning is shared by all parties involved in the communication process, as we see here, subject to some convention. Okay, some convention, some meaning, okay, that are shared by all parties, by a community, okay, involved in this communication process. So properties of representations. Humans have many different ways of perceiving representations, which are also used in our communication with computers. Okay, with your computers, you will use your perceiving, okay, your senses, okay, or your sensing to perceive these representation. So we have the auditory representations are perceived as sound. So the human use music or spoken language. The computers use alarms and beeps to attract human attention. Okay, so this is one way of perceiving. Visual representations are perceived as sight. So human use written music, language, traffic signs, flags, painting, okay? And computers use scanners to see images and the screen to communicate visual images, okay? So this is the way of computers to for visual representation. Tactile representations are perceived by touch. So humans with visual and hearing, impairments use various languages that rely on touch. The case with Braille language. Okay, so it will focus on touch. Okay, why? Because these humans, okay, will have problems, will have impairments related to visual and hearing. Okay, so it will use their touch. Okay, their tactile. Okay. representation. And computers use keyboards, joystick, vibrating eye mice. Okay, all this to show. Okay, to represent. Okay, some activities. Okay, or some uses. Okay. Okay, and almost any analog quantity can be represented digitally. Okay, so we can represent any analog quantity using, okay, some representation. We will see that. So this means that the representation can be stored and manipulated by computer with the values of digital representation being coded. There will be some coding as binary numbers that can be stored. So we will now focus or discuss on how digital codes are used to represent images and sounds now. Okay, so we have already seen how we can represent the analog. Okay, it is a continuous variable. Okay, it continuous values. Okay, and we can measure this value and make some chart. Okay, but now we will focus on digital codes. So look at the representing images, how we can represent images. So on a computer screen, images are generated by dividing the display into a large number of tiny units called pixels. Okay, so this is the unit of your screen. When you have your screen, computer screen, you need to focus on the number of pixels. Okay, the more the number of pixels, the more the resolution of your computer will be. Okay, so each pixel can be displayed in a number of different colors and levels of light, intensities, and brightness. Okay, so it will have some codes here that will show the number of different colors, the level of light, intensities, or brightness. So the greater the number of pixels used for a given size of display, the more detail can be displayed and the higher quality of the image will be. Okay, so this is the relationship between the number of pixels and the more details and the higher quality, okay, of the image. Okay, so to begin with, we will look at the representation of black and white images. So let's consider an artificially small scale example. It is a display using 8 rows of 16 pixels displaying a triangle. Okay, so here we have 1, 2, 3, 4, 5, 6, 7, 8 rows. And here we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, 16 columns with 8 rows, and this is my screen. Okay, so in this screen I will have how many pixels? How many pixels? It will be the number of the column multiplied by the number of the rows. Okay, it will be 16 multiplied by 8. So we will have 128 pixels. The pixels here is this square. Okay, the number of square here. So as you can see here, we have how much black square? We will have 1, 2, 16. This is 15 because here this is 16. So 15, 16, 17, 18, 19, 12, 20, sorry, 21, 22, 23, 24, 5, 6, 7, 8, 28. So we will have 28 black square and we will have 108 100 white square. Okay, so this is the representation. So if we represent a white pixel by the binary 0 and the black pixel by the by bit 1, we can code the image and convert it into a set of binary 1s and 0s that we would store or transmit. So you can see here, this is the triangle with black. So all the black will be in will be coded by 1. Okay, sorry. This is my 1. Sorry. Okay. So this is my triangle. Okay. And the other squares will be represented by 0. Okay, so this is one representation. The display system described so far is very simple, but quite restricted. Okay, by increasing the number of pixels, we can improve the amount of detail the image contains. Okay, its resolution, it means, and get high quality black and white images. So this sort of encoding is referred to as a bitmap or raster graphics. Okay, this is this sort of encoding. Okay, it is called bitmap or raster graphics. Okay, are you with me? Okay. Okay. So instead of using now just 1 bit, if you use 2 bits for each color, in this case we will have 4 possible codes. Okay, so representing 4 colors. Okay, so we will have, because we have used 2 bits, so 2 power 2 is equal to 4. We will have 4 combinations. Okay, we will have 4 colors. Okay, so this is the 4 colors: 00 for white, 01 for red, 10 for blue, and 11 for black. Okay, and binary coding can be extended to represent an increasing range of colors. So this is my picture now. For 8 colors, we need to use 3 bits binary word. Okay, so it will be 2 power 3 is equal to 8. So we will have 8 colors. 8 combinations to represent 16 different colors, so we need 4 bits. Okay, so this is how we can represent the pixel, okay, with more details, okay, with more colors. Okay, so look here for the black line here, black is 1 1, so all this line will be 1 1, just the last square. After that, we will have the blue. Okay, so the blue 1 0. This is 1 0. The blue. Okay, this is the red. For the red 0 1, it will be 0 1. Sorry, until here the blue, and from here the red. This is the red. Okay, and this is the black. And the others will be the white. Okay, 0 0. Okay, so a set of a given number of bits used for data representation is called binary word. Okay, what is a binary word? It is the set of a given number of bits. If we use 2 binary words, it means that we have 2 bits. Okay, if we use 4 binary words, it will have 4. Okay, so an n-bit binary word can represent 2 power n different options. This is 1 bit binary word. 1 bit means black and white. Okay, 2 bits binary word can be represented by 2 power 2 is equal to 4. So the blue, the white, the red, and the black. Okay, so look at this example. To code 300 colors. Okay, 300 colors. So we need to write 300 in the form of 2 power, okay, something. We need 9 bits word length, okay, binary length. Okay, we need 9 bits. Why we need 9 bits? 2 power 9. How much 2 power 9? 2 power 9, it will be equal to 512, okay? And if we use 2 power 8, so 2 power 8 is equal to 256. It is lower than this number. So there are some colors that will not be displayed or will not be represented, okay? This is why we need to use 2 power 9. We need to use 9 bits, okay, to represent these 300 colors. Even if there are some bits that will not be used, okay, but we can represent all these colors, okay? Is it clear? So any coding scheme that allocates a binary code to each pixel in order to define its color and brightness is called a bitmap. Okay, it is called what? A bitmap. What is a bitmap? It is a coding scheme that allocates a binary code to each pixel in order to define its color and brightness. Okay, so this is the bitmap. And what is a file formats now? File formats are agreed upon standardized way of organizing and storing the binary data that represents an image in your computer. Okay, this is how you can organize, how you can store your binary data, okay, that represent this image in your computer. It is called, okay, file formats. Okay, are you with me? So you need to keep in your mind these keywords: the binary word, the bitmap, the file formats, okay? And here we have the raster graphics, okay, etc. Look now at these, because bitmap files are relatively large, the bitmap files are relatively large, so they will be not the most appropriate choice of format for images to be viewed on the web. You know that on the web you have a huge amount of data, okay, and if you the image is very big, okay, it will be charged, okay, after some times, okay, it will take time to be loaded, okay. So this is why we will use other techniques such as the JPEG, okay, the JPEG, which use information about human perception to reduce the file size. Okay, it is the JPEG. It is a reduced format of the image. Okay, instead of using the bitmap files, which will take all the details about the image. Okay, there are some other techniques that will reduce this file size, this format files. Okay, they still assign binary codes to pixels, but in a different way and are not usually called bitmaps, okay? So it will be called vector graphics. Vector graphics is a coding image technique. Instead of sending or storing information about each pixel, information about the different shapes in the image is used, okay? We will not store all these details about about each pixel. We will rather store information about different shapes, okay, in the image. This is what will be stored in your website, okay, to be loaded quickly, okay, to be loaded fastly. So vector graphics now are most appropriate where the image is made up of regular shapes, as in many web or computer some game graphics. Example, a straight line can be defined by its starting and end points, a circle by its center and radius, okay, etc. In this way, the file size can be kept much smaller than the bitmap, and provided the complete graphic consists only of the shape allowed within the vector graphic system. Okay, so you see the difference between these vector graphics and the bitmap, okay, files. In the vector graphics, we will keep these files as small as we can, okay? comparing to the bitmap file. We will not take all details about the pixels and the colors and the brightness, okay? We will take the shapes, okay? We will take the regular shapes, okay? We will reduce this size, the size of these files. So it is also easy to produce simple animations of such shapes for images such as photographs or motion pictures. The vector graphics approach is not effective, okay? So once you need to use some motion pictures or some photographs, okay, you will not use this vector graphics, okay, because it is not effective. There are some details that will be lost, okay, after that, okay. So this is the, okay, so this is all about the images and how we can display or how we can represent the images in a computer or in a digital world, okay. So there are some real world applications like the computer's memory and hard drive is measured in bytes. What does it mean bytes? It is 8 bits, kilobytes. It is written in capital, okay, K and B. It means that it is 124 bits or 2 power 10 bytes, okay. The megabytes, it is 124 kilobytes and it will be 2 power 20 bytes, and the gigabytes is 124 megabytes and it is 2 power 30 bytes, okay, 30 bytes, okay. So look at this first question. A smartphone has a screen resolution of 640 multiplied by 960 pixels, okay, so this is the resolution. We write the number of rows multiplied by the number of columns, okay. How much data in bits, bytes and megabytes is required to display an image if it uses 16 bits for each pixel, okay. So look now, you will have 16 bits for each pixel and you will have the resolution, so you can calculate the number of pixels, okay. So this is how we calculate the number of pixels from the resolution. It is the multiplication of the number of rows by the number of columns. It will be equal to 614 and 4,400 pixels, okay, in the total. And the number of bits will be, because every pixel, look here, 16 bits for each pixel, so we will multiply the number of pixels by the number of bits required for each pixel. It will be this number. After that, we need to convert from bits to bytes, so we need to divide by 8. And we need to, from bits to megabyte, okay. So we need, or from bytes to megabytes, we need to divide by 2 power 20, okay. So it will be equal to 117 megabytes, okay. So this is the data, okay, of to display an image if each pixel will consume 16 bits, okay. Is it clear? Are you with me? Do you have any question here now? Clear? I need your feedback. Okay. Okay. Look at this second question. Consider now an image of size 100 multiplied by 240. Okay, so this is the resolution of this image. Okay, how many bits and bytes are required to store this image inside the computer? Okay, using only 2 colors, it means 2 bits. Okay, 1 bit for every color. Using 3 bits per pixel in grayscale model and using the RGB model. Okay, so here you have 3 options, okay, of representing the colors, okay. Okay, in the first we need what? We need to calculate the number of pixels. This is the first step, okay. So how we can calculate the number of pixels? It is the multiplication of the number of rows by the number of columns. This is the number of pixels, okay. For this number, if we use the black and white images, so only one bit is used to represent a pixel, okay. So the number of bits needed to represent this image is the same of the number of pixels. And if we need to convert in bytes, so we need to divide by 8. So this is the number of bytes, 3000 bytes, okay. If we need to convert this number to what? To megabyte, we need to divide by 2 power 20, okay? By 2 power 20. But here it is, you are not asked to do that, okay? Here for C, you will use 3 bits per pixel to represent a pixel. So you will multiply the number of pixels by 3. This is the number of bits. And after that, you will divide this number by 8, okay? Because every 8 bits will constitute a byte, okay? So this is the number of bytes, 9000. And for the RGB, look now, for the RGB model, we will use 24 bits. Keep it in your mind. Once you are asked to represent or to calculate the number of bits when using RGB model, it means that you will use 24 bits to represent each pixel, okay? So the number of bits needed to represent this image is the number of pixels multiplied by the number of bits for each pixel, okay? It will be a great number. And the required number of bytes is the following number, okay? Divided by 8, it will be equal 72 thousands, okay, of bytes, okay? So it is a great number, okay? So you can see this is why when you have a good quality with good colors and brightness, okay, so you will have much more data, okay, so you will have a great number, okay, of bits and bytes, okay. Move now to the question number 3. So a file in bitmap format is 3 megabyte now inside. So now we have the format of the byte, the bitmap format, okay, the file is 3 megabyte, okay, bytes inside. How long will it take to download the file from the internet if my internet connection is running at 14.1 megabit per second? Megabit per second, okay? So you will have, as you can see here, you have different units. Megabit per second, megabytes, okay? So before solving the question, you need to know the file is 3 megabytes, while the internet speed is in megabits per second. So in order to calculate the time taken to download, we must to convert the values to bits, okay? We need to make all these numbers with the same unit, okay, which is the bits here, okay? So in the first, you will convert the 3 megabyte, okay? So the megabyte is 124 bytes, is 124 another time, okay, kilobytes and bytes and bits, okay? So this is for bits, this is for bytes, kilobytes, and this is for megabytes, okay? So this is the number of bits. Look at this huge number for this bitmap file. This is why the bitmap, okay, format is replaced by the JPEG format in the websites, okay? Because to make these the file size smaller, okay? Okay, now look at the internet speed. So the internet speed is megabits per second, okay? Mega, here the mega is 1000, sorry. okay? And the bits here, okay? So you will have the mega from, this is the kilo bits and this is the megabits, okay? So this is in bits per second, okay? And using now the formula of time, so the time is equal to the size divided by the speed, okay? Because we have the speed is equal to the size divided by the time, okay? So if you need the time, you need to see the size. This is the size and this is the speed, okay? So this speed is equal to the size divided by the time. Once you don't have the size, so you need to multiply the speed by the time. And once you have the speed and you have the size, so you need to divide the size by the speed to get the time. Okay, so here we need the time. So it will be equal to the size divided by the speed. This is the size, okay, in bits. This is the speed in bits per second, okay? So this is the time. The time will be 1 second, 0.78, okay? Is it clear? Yes, here megabits here, the megabits here, the mega here is 100. It is not the mega as the computer science, okay, the computer units. It is here in mega in numbers, okay. This is in decimal number, okay, in decimal system, and for this it is the binary system. Yeah, the mega is, yeah, this is, yeah, this is the mega is 10 power 6. This is 10 power 6. Okay, 10 power 3 for the kilo and another 10 power 3 for the mega. Okay. Okay, it is the same. Okay, so this is 14.1 multiplied by 10 power 6, the mega. Okay. Okay, do you have any question now? Are you with me? Any question? No questions? Any question? Is it clear? So the most important step here is to convert in the same units, okay? Once you have many units in your question, megabits by megabytes or gigabytes, whatever, on byte and whatever, okay? So you need to keep all these units in the same unit, okay? To convert these values to the same unit, which is the simplest one, is the bits, okay? The bits, okay? Or the bytes, if you need the bytes, okay? Okay, move now to the question number 4. So a common bitmap format for displaying reasonably high quality digital images is to use 24 bits for each pixel. So this is the RGB, okay? The RGB representation. When we have 24 bits for each pixel, it means that we will use the RGB, okay? So how many pixels are required for 1024 multiplied by 768 screen resolution? And how many bits of data does this require for each image? Okay. After that, you have your internet connection that provides an upload speed of 2.3 megabits per second. Okay. How long will it take to upload such an image? So you need to resolve your problem step by step, okay? So in the first, you need to calculate the number of pixels. As you can see here, the number of pixels is the number of rows multiplied by the number of columns. So this is the total number of pixels, okay? After that, you need to calculate the number of bits of data. Because every bit will require 24 bits every pixel will require 24 bits, okay? So we will multiply the number of pixels by 24. This is the number of bits, okay, required, okay, to display, okay, or to display this image in this screen resolution, okay. Now we look to the upload speed is 2.3 megabits per second, so we need to convert this mega, just this mega, it is to multiply 2.3 by 10 power 6, okay, and we will use the same formula. The time is equal to the size divided by the speed. So this is the size, the number of bits, and this is the speed converted in bits, okay, per second, and this is the time, okay. So it is 8.21 seconds, okay. It will take, okay, 8.21 seconds to upload this image using an internet connection, okay, of upload speed about 2.3 megabits per second, okay. Is it clear? Is it clear? Do you have any question? Do you have any question? Okay, clear? What? Megabits? Yeah, per second, yeah. There are some who write per seconds, P, and there are someone who cannot write this, okay? It is the same, okay? Okay, okay. Move now to representing videos now. So a video or a movie is a series of images called frames that slightly differ one from another, passing them one after the other at certain speed. Frame rate, called frame rate, will give the illusion of movement. Okay, so this is how we can create a video or a movie. It is a series of images. These images are called frames, okay, that slightly differ, okay, there are slightly difference between these frames, and these frames will be passed, okay, one after the other at certain speed, okay. So this is the frame rate. It is called, this speed is called frame rate, will give the illusion of movement. So this is will give the illusion of movement. So the frame rate is the speed of flipping the frames one after the other, okay. So we have some films that films are usually shot and displayed at 24 frames a second, frame per second, okay, 24. This is the speed frame or frame rate of the films, okay. The TV pictures are represented between 25 and 30 frames per second, depending on what country you live in. And the high definition TV currently only available in Japan, okay, so uses 60 frames per second, okay. There are some high definition TV, okay, that uses a high frame rate, okay, it is 60 frames per second. So look at this, at this question. Consider a 2-hour film. This is the duration of film to be displayed on a computer at 24 frames per second. Okay, this is the frame rate, which each frame is 640 multiplied by 380 pixels. This is the resolution of your frame. and will be represented using 24-bit RGB color encoding is being used. Okay, so how many bytes will be required to represent the whole film? How many bytes it will be required, okay, to represent the whole film? For the answer now, so we will start by the number of pixels in one frame. In one frame, we have, this is the number of pixels, okay? The number of bytes needed to represent one frame, okay? So in the first, we need to multiply this number of pixels by 24, okay, the number of bits. And after that, because we need in bytes, so 24 divided by 8, it will be 3. Okay, so this is where 3 comes, okay? It is multiplied by 24, the number of bits for each pixel, and divided by 8 to have the bytes in bytes and not in bits, okay? Okay, so this is the number of bytes. After that, we need to calculate the number of seconds in 2 hours. So as you can see, 1 hour you will have 60, okay, minutes multiplied by 60 seconds in every minute. So this is the number of seconds in 1 hour, 3,600. And because we have 2 hours, so it will be multiplied by 2, it will be equal to 7,200 seconds. The number of frames now in 2 hours, so it is the number the number of seconds multiplied by the frame per second, okay? So I will have this number of frames, okay? Now each frame is represented by this number, okay, of bytes. So the total number of bytes needed to represent the whole film will be equal to this number, the number of frames multiplied by the number of bytes needed to represent one frame. And if we need to convert this number to gigabytes, okay, so we need to divide by 2 power 30, okay, and this is the number of gigabytes or the data, okay, the number of data to represent this film, the whole film that takes 2 hours, okay? So it will be 117.416 gigabytes. Okay, is it clear? So just you need to practice, okay? You need to know the steps, how many pixels, how many bits or bytes to represent this frame, okay? How many frames after that you have in your video, how long your video will take, okay? And after that you will calculate, you will multiply the number of frames by the number of bytes, okay, needed. Where did we get the 2 from? Where? This 2, this one, 2 hours. This 2 for 2 hours, okay? Because consider a 2-hour film. So your film will take 2 hours. We need to convert this 2 hours in seconds. So it will be 7,200. This 3, it is from 24 divided by 8. Okay? This is the number of pixels. We need to multiply the number of pixels by the number of bits for each pixel. And to convert it in bytes, we need to divide by 8. Okay? Is it clear? Are you with me? Do you have any question? Any question? No? Clear? Okay, I hope so. Okay, move now to the sound, to the Audacity. Okay? Okay, so the Audacity is sound editing program, or okay, to record and manipulate sound, okay, as you can see here in this figure 8. So it is available for computers using Windows, Macintosh operating system, or Linux operating systems. Okay, you can store, you can record And the program allows you to load, to record, to save and play sound using different file formats to look at the waveform of sounds and to edit sounds, okay? So this is how we can manipulate these sounds. So the sound is another feature or is another analog feature of the world. If you shout, okay, hit a piano key or drop a plate, then you set particulars of air vibrating and your ears will interpret this vibration as sound, okay? So this is what does it mean by sound in reality, okay? There are some particles of air vibrating, okay? And your ears will interpret this vibration as sound. So the sounds we hear generally consist of small rapid movements of the atmospheric air pressure that surrounds us, and vibrating a tuning fork makes pure sound that makes particles of air move backwards and forwards with the fork, okay? So one way to visualize this waveform is to draw a graph of how far an air particle moves backwards and forwards as time passes. Okay, the graph of typical waveform, okay, is shown in this figure. Okay, so this is the typical waveform. It is typical, okay, it is perfect, okay. So as you can see here, we have a cycle. So what does it mean, a cycle? A cycle represents the time between adjacent peaks. Okay, this peak, okay, for example, and this peak, and this period is called cycle, okay? And the number of cycles completed in a fixed time, usually a second, is known as the frequency. So what is the frequency? Is the number of cycles per second, okay? The amplitude of the wave, this is the amplitude, okay? It is the maximum displacement determines how loud the sound is, okay? The frequency now decides how low or high pitches the note sounds to us. And note that this figure is theoretic, okay? In reality, the amplitude will decrease as the sound fades away. This is the reality. The reality is like that, okay? The amplitude will decrease until it raises to 0, okay? This is the reality. But the blue line here, it is theoretic, okay? It is not real. It is in the perfect world, okay? And we don't live in a perfect world. So in our world, the reality is the reality. The amplitude will decrease, okay, as the sound fades away. Okay, a tuning fork now is a very simple instrument and so makes a pure sound, okay? So real instruments and real noises are much more complicated than this, and an instrument like a clarinet would have a complex waveform. This is as shown in figure 10. A drop plate would have a irregular waveform. This is irregular. Here we have cycle. It will be repeated. Here we don't have cycles, okay? Why? Because we have irregular waveform. This is regular waveform, okay, the blue one. The blue one is regular, okay? We have the same amplitude in the, okay, the same cycle, the same peak, okay, after the same time, etc., okay? Okay, now sound sampling and storing. How we can manipulate these sounds, okay? So a microphone is used to convert the sound pressure wave into an analog electrical signal, okay? It is an analog signal. So this signal needs to be converted or coded into a digital representation. Okay, the process of digitizing a sound includes two stages, which is sampling and quantization. Okay, so this is the process of digitizing, of how to make the wave or the analog wave sound wave, okay, into a digital one, okay, a digital signal. As we split up images by dividing them into pixels, we can split now a sound wave up by dividing it into very small time intervals called samples. Okay, this is sampling. From the sampling process, we will have different samples. So the first stage of the process is to measure the amplitude of the sound wave at regular time intervals, taking readings like this. This is called sampling. And the number of times per second we take a sample is called the time or the sampling rate. We will talk the tuning fork example, set an interval of 0.5 seconds and look at the state of the wave every 0.5 seconds as shown in figure 11. Okay, so look at this figure. Okay, I take this first sample and after this is at 0.5. Okay, at 1 I will take another sample. At 1.5 I will take another sample. So this is my samples. And the sample rate here, the sampling rate here is 0.5 seconds. Okay, every half second. Okay, I will take the sample. Okay, so this is what does it mean, sampling process. Okay. So reading of the amplitude of the wave at every sampling point gives the following set of numbers. So we will have this number 9.3, we will have this number minus 3.8, we will have this number minus 4.1, 8.2, minus 10, here 4, here 4.5, etc. So this is my sampling, okay, sampling numbers, or my samples. Okay, if we plot now, this is my sample. If you plot a new graph from the waveform using just these numbers, we get the graph in figure 13. So this is how we convert from this analog signal to a sampling, okay, discrete, okay, a digital one, okay, which has discrete values now. Okay, so this is from 0.5 to 1 seconds, it will be 9.3. After that, minus 3.1, minus 4.1, here 8.2, here 10, here 4, and here 4.5. Okay, so this is the plateau at every sampling point represent the intervals between samples where we have no information and no assume that nothing happens. Okay, so we assume that at this stage of time, at this period of time, we have only this value. Okay, this means that the audio signal produced by the sample does not closely follow the original signal, leading to poor quality sound. Okay, so as you can see here, we have many information that will be lost. Okay, because we have here a bad sampling rate. Okay, so how we can improve sound quality? By making our sampling interval smaller. Okay, when we have a smaller interval of sampling, we will have much more samples, and we will have many details. Okay, in this sample, so we don't lead to details or to sound loss. Okay, losses. So figure 14 shows sampling a sound wave at interval of 0.1 seconds. Look now, at every 0.1 seconds, okay, we will take samples. We will take samples, okay. So we will have, as you can see here, we will have, okay, the approximate shape of the waveform, okay. So we don't have here many detail that will be lost. So here we will be more effective. Okay, so figure 15 shows the digital conversion of figure 14. So these samples, I will write these samples, okay, in Plato. And after that, we need the quantization. Okay, from sampling, we will go to the quantization, which is the second stage. It is the process of converting each sample into a suitable number for computer. Now these numbers, as we have, we will store these numbers for computers. So we will convert these numbers to digital one using the 0 and the 1 by dividing the maximum voltage range of the analog sound signal into a number of discrete voltage bands. Okay, so here, for example, we can use three bits. Okay, so the result is a string of numbers at regular intervals as shown in figure 16. Okay, so we will show here, because here we have the 8. Okay, so 8, it can be represented by 1 1 1. Okay, 8. Okay, 8.2. Okay, so this is how we can represent. Okay, after that, this number, okay, is represented, for example, by this stage. Okay, so I have some stages and I need to do some quantization, okay, about these samples. Okay, so if we want to just send sound somewhere, then we can simply send the string of numbers along a suitable transmission channel to a digital to analog converter and loudspeaker at the other end. Okay, so here we have what? We have the microphone. This is my microphone. I talk here in this microphone. So the sound will be sampled. Okay, so there are some sampling. After that, quantization. This quantization will lead to a string of 0 and 1s. For example, this one. Okay, this is my channel. Okay, transmission channel. At the receiver, I need here a digital to analog. Okay, it will take this 1 0 0 1 etc. and will convert this digit to analog. Okay, and after that, if you have a loudspeaker, okay, you can have this sound. Okay, this is my sound that I will send from here. Okay, so this is digital to analog. It is the invert. Okay, the conversion from digital to analog. So we will have this quantization, the inverse. Okay, from numbers code to real number, from real number to samples, from samples to the waveform. Okay, and any device that can store large quantities of numbers can be used to store sound, so such as modern music players, your phone's internal memory, and any devices that contain a standard hard drive. Okay, so look at this question. For 4 seconds of single channel storage, suppose that each sound sample requires 2 bytes of storage, and that an additional 44 bytes are needed for formal information about the sound. If the sampling rate is 44,100 samples per second, what is the size of the file you would expect? Okay, are you with me? Is it clear now? Now you need to calculate the number of, or the size of this file. Okay? Okay, in the first, we have the sound in the file is 4 seconds long. Okay? And we have the sampling rate is 44,100 samples per second. So we can calculate the number of samples. Okay? The sampling rate is equal to the number of samples. Okay, multiply it. Okay, it is the size multiplied by the divided by the time. Sorry, here now we have the sampling rate and we have the time, so we need to multiply this one by this one. Okay, so look, the sampling rate is 44,100 multiplied by 4 seconds. So we will have this number of samples. Okay. Okay, now for each sample will require 2 bytes of storage, and an additional 44 bytes are needed for formal information. So the file size will be the number of samples multiplied by 2 bytes plus 44 bytes for the formal information. So this is the number of bytes. This is the size of this file, okay, in which you will store these samples, okay, taken in a period of 4 seconds. Okay, is it clear? So you will process step by step, okay, to understand the problem. Okay, are you with me? It means that there are some information, okay, about the shape, for example, okay, how it can be the shape, whatever, okay. These for information, okay, it is for the communication, okay, about the communication process. Okay, now move to the compression of digital files. Okay, the digital encoding of sounds, images, and especially video produces large data files. As you can see, we have large data files, especially when you have a video, okay, sound and images. So for example, a 500 pages text document created in plain text format in Microsoft Word is 1.8 megabits, okay, megabytes, whereas a simple 3-second long video may be 186 megabytes. So you can see the difference between texts, between images, and between videos, okay? So we need some compression, okay, to keep these data files as smaller as we can. Compression means taking the original digital file and converting it into a new file that uses considerably fewer bits without significantly degrading or corrupting the quality of the original content, okay? So we will make some compression, but without making significantly decryption, okay, or corruption of these videos and images, okay? So this results in saving the memory needed to store the data and increasing the speed of transfer. So the ratio between the uncompressed file size and the compressed file is known as the compression ratio, okay? So the compression ratio is equal to the size of the original file divided by the size of the compressed file, okay? So the higher the compression ratio is, the less storage space would be needed for the resulting compressed file, okay? So look at these examples. If 10 megabits bytes file is compressed to 2 megabytes, so the compression ratio is 10 divided by 2, okay? Which is equivalent to 5 divided by 1, okay? So if the same file is compressed to 5 megabytes, the compression ratio will be 10 divided by 5. It will be equivalent to 2 by 1, okay? So you can see you can see here the size, okay, that we can the less storage, okay, space that we can need, okay? So main types of compression. We have the lossless compression and the lossy compression, okay? So what does it mean, the lossless? Lossless compression techniques do not lose any significant aspect of the original representation, but the lossy compression loses parts of the original in a controlled way, okay? So this is the two types of compression. We have some compression techniques that will preserve all the significant aspect of the original representation, and we have the lossy compression, in which there are some parts that will be lost, okay, but in a controlled way, okay? There are some ways for this loss, okay, loss of information. The reverse of operation of the compression is called decompression. Decompression is the reverse operation where the redundant parts are put back into the representation to restore it to its initial form, okay, to restore the original file. Okay, let's look at the lossless compression. So as I said, The lossless comparison, the digital data is stored in a compressed form such that it can be recovered sample from sample with nothing altered or lost. Okay, so this is the lossless comparison with nothing lost or lost. It is like a computer zip file. So the computer zip file is an example of lossless compression of digital data. We will not lose there are no loss of any bit or sample. Okay, we have a powerful form of lossless coding is called dictionary based coding. Okay, so in most digital files, some data is repeated over and over again, and a compression algorithm simply gets rid of this redundancy by scanning for patterns and translating those patterns into something that takes up less space. Look at this example. We will use the following test to demonstrate how dictionary-based coding compression works. So look, when the going gets tau, the tau get going, okay? So there are 9 words. 1, 2, 3, 4, 5, 6, 7, 8, and 9, okay? 8 spaces. 1, 2, 3, 4, 5, 6, 7, 8. And 2 punctuation symbols, which is the comma here and the point. So a total of 47 characters is using in this phrase, okay? If 1 unit of memory is allocated for each character, the file will consist of 47 units, okay? Look now, here the get or the going and the to, okay, are repeated. So our dictionary of words looks like, okay, 1 for the, 2 for going, and the 3 for this to. So the sentence can be now expressed as when 1, 2 gets 3, 1, 3 get 2, okay? So thus the original sentence uses 47 units of memory while the compressed version using only 27, okay? Now we have reduced the number of characters, okay, by this sample, okay? Another technique now for lossless compression is called run length encoding. So in this compression method, runs of similar data items are recognized and replaced with a single instance of the data item, together with a number indicating how many times the item is repeated. So for example, the stripped pattern in figure 17 can be represented by the binary sequence, okay? 01, 01, 01, etc. And the sequence repeated 01 7 times. This can be represented in run length encoding and 7 01s. Okay, so this is another technique of compression. It is a run length encoding. Okay, this one is a dictionary based coding, and this one is the run length. Okay, encoding. Okay. Look at this example now. The pattern in figure 18 can be represented by binary strings. So for the ones, it will be for the black it ones, for the white is 0. So we will have 8 ones. Okay, this 8. So 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 by multiply by 5, it will be equal to 80 ones. Okay. After that, we will have 28 zeros, this black or this white, and 20 ones. Okay. So this is how we can represent in run length encoding 81, 28, 0, 21. This one. Okay. So this long file, okay, will be small, okay, by this representation. Okay, so lossless coding is used in a similar way for simple images such as line drawings and simple shapes in the GIF, okay, graphics interchange format, used for images on websites. Okay, so this is one way to use, okay, to compress the images in the websites, okay, using the GIF, okay, GIF, okay, format, okay. Is it clear? Are you with me? Okay, move now to the lossy compression now. So in the lossy compression, the original file is processed in a way that preserves the important information, but discards other information that is less important for particular application. Okay, example of this lossy compression. So for the lossless compression, you have the GIF, okay, and for the lossy compression, you have the JPEG, okay, the Joint Photographic Experts Group, the JPEG. So lossy compression of audio, image, and video files exploits features of a human perception to reduce the amount of data. Psychoacoustics is the study of how humans perceive and respond to sound, and the knowledge from psychoacoustics is used in lossy compression techniques to reduce the amount of information a sound signal contains without affecting the perceived sound. Okay, so there are some particles of sound that the humans cannot perceive, okay, or that the humans cannot care, okay, so that it will be eliminated, it will be discarded, okay, to reduce the number of bits or the size of this file. So the MP3 audio compression offers acceptable audio quality with a high compression ratio in the region of 11:1, okay? So rate 11:1, okay? This is the compression ratio of the MP3. Okay, now for the digital image compression now, as described before, a digital image is made up of multiple small elements known as pixels. So the more pixels there, the higher is its resolution, but the greater is the memory space required. So there are two solutions to reduce the amount of memory required, reduce the number of pixels required, and compress the data using compression software, okay? So one of the most important standards for photo image coding okay, no problem, Firas. Also used as part of MPEG video is the one produced by JPEG, okay? So we have some MPEG video, it is compressed format of videos. This compression technique will divide the picture up into small blocks of pixels and performs complex calculations to arrive at a concise description of the block. So it will remove or reduce some components because they are not important for human vision, okay? There are some parts, okay, that we cannot differ, okay, our size is not, okay, cannot perceive this difference, okay, so it will be discarded or it will be eliminated. Okay, move now to the number systems. So as you I don't know if you have already see that in T03 Tm111 or Tu170. Okay, so we have different number systems, the decimal one, the binary one, the octal one, and the hexadecimal. Okay, so the decimal base, the well-known decimal system, okay, base 10, so it uses the 10 symbols from 0 to 9. The binary, which base is equal to 2, so it uses only 2 symbols, the 0 and the 1. The octal, okay, which base is equal to 8, so it will use 8 symbols from 0 to 7, and the hexadecimal, which uses 16 symbols, okay, from 0 to 9 and from A to F, okay. So A for 10, B for 11, C for 12, D for 13, E for 14 and F for 15. Okay. Look now at this, the first decimal, base 10 system. The system is used worldwide. It uses the 10 digits from 0 to 9, and each column counts groups 10 times bigger than those counted in the column to its right. So 37, look at this, 37 in, in fact is equal to 7 plus 3 multiplied by 10 power 1. This is 7 multiplied by 10 power 0. It is equal to 1. 345 is equal to 5 multiplied by 10 power 0 plus 4 multiplied by 10 power 1 plus 3 multiplied by 10 power 2. The 4,621, 1 multiplied by 10 power 0 plus 2 multiplied by 10 power 1 plus 6 multiplied by 10 power 2 plus 4 multiplied by 10 power 3. For the octal now, this is the octal. So the octal is mostly used by computer scientists. It uses 8 digits from 0 to 7, and each column counts groups 8 times bigger than those counted in the column to its right. So look at this number, how we can convert from 8 to 10 from the octal system to decimal system. So it will be equal to 6 multiplied by 8 power 0 plus 4 multiplied by 8 power 1. So 6 plus 32 is equal to 38 in the decimal system. 125 in the octal system is equal to 5 multiplied by 8 power 0 plus 2 multiplied by 8 power 1 plus 1 multiplied by 8 power 2. So it will be equal to 64 here plus 16 plus 5. So 85 in the decimal system. For the binary now, binary system. All question about TMA, I will see your questions at the end of this tutorial. At the end of this tutorial, I will answer to your question about TMA. Muhammad. Base 2 now. The system that is used by the computer. It uses 2 digits, which is 0 and 1, and each column counts groups 2 times bigger than those counted in the column to its right. So, for example, this number 110 base 2 is equal to 0 multiply. I will answer to your question at the end of this tutorial. At the end. So it will be equal to 0 multiplied by 2 power 0 plus 1 multiplied by 2 power 1 plus 1 multiplied by 2 power 2. So this is 2 and this is 4. It will be equal to 6. This number 1 multiplied by 2.2 power 0, 0 multiplied by 2 power 1, 1 multiplied by 2 power 3 by 2 power 2, sorry, and 1 multiplied by 2 power 3. So 8 plus 4 plus 1. It will be 13 in the decimal system. So the number system. So the bit is the short format. For binary digits, it will refer to 1 or 0 stored in the computer. A byte is a group of 8 bits, can be used to represent numbers between 0 and 255. A byte looks like this. The largest number we can store in a byte is 8 ones, which equal to 255 in the decimal number. Decimal system. And the smallest number we can store is all zeros. It will be equal to 0 in the decimal system. Okay, so the word size for a computer is the number of bits that the CPU of a particular computer can handle at one time. This is the word size. Okay, it is the number of bits that the CPU can handle at one time. And when the word size of a computer is 32 bits, it's equal to 4 bytes. So the largest binary number that the computer can process in a single operation would be, okay, 4 bytes with ones, okay? So 32 ones, okay, which is in decimal will be equal to this huge number, okay? So this is in one single operation. It can be handled, okay, by the computer. Okay, now to convert from binary to decimal, a method known as positional notation can be used. So the below figures illustrate the method with an example of how to convert 10011011 to decimal. So this is the number, okay? So step number 1 is to list the powers of 2 from right to left. Start at 2 power 0, evaluating it as 1, this one. Then write the binary number you want to convert below the list. So this number, this is my number, and this is the power of 2. Okay? Okay. So look, step number 2. I will draw lines starting from the right to connecting each consecutive digit of the binary number to the power of 2 that is next to the list above it, okay? After that, step 3, move through each digit of the binary number. If the digit is a 1, okay, write its corresponding power of 2. If the digit is 0, write a 0, okay? So look here. Here, this is the corresponding is 1, so write the number. Here 0, write 0, okay? Here is 1, write the number. Here is 1, write the number. Here is 0, write 0, okay? So it will be 100, and the sum should be 155. This is the decimal equivalent of the binary number, okay? So you can use this method, okay? This method, positional notation, to convert from binary to decimal, okay? Okay, move now from octal to decimal. So to convert from octal to decimal, the following formula can be used. So it will be equal to each, okay, coefficient multiplied by 8 power its position, okay? So when A is the individual digit being converted, while I is the number of the digit counting from the rightmost digit to the number starting with 0. So look, convert this number into decimal. So it will be 5 multiplied by 8 power 0 plus 6 multiplied by 8 power 1 plus 7 multiplied by 8 power 2. Okay, so this is the result. Here, 6 multiplied by 8 power 0 plus 3 multiplied by 8 power 1 plus 3 multiplied by 8 power 2 plus 1 multiplied by 8 power 3. Okay, so this is the result here. From decimal now to binary. One of the easy methods used to convert from decimal to binary is comparison with descending powers of 2 and subtraction. Okay, so converting, look at this example, converting the decimal number 156 to binary, sorry, is shown below. 100, okay, so this is your number. Okay, so you have, for example, 156. So 156 is greater than 128, so I will carry the subtraction, okay, and I will get the result, okay, the remainder. So here, because I have this one, so I will write 1, and I have 28. So 28 is louder than 64, I will put here 0. Is louder than 32, I will put here 0, okay? but is greater than 16. So I will put here 1 and I will do subtraction from 16. I will have 12. So 12 is greater than 8. I will write here 1 and I will subtract the 8. I will get 4. So I will subtract the 4. I will get 0 and 2. So 0, it is lower than 2 and lower than 1. So I will write 0, 0. So this is the answer. Okay. This is how we can use the subtraction. For the subtraction, so this is my number, okay? And I will compare this number with the greatest one, okay? With 2 power here 5, okay? No, 0, 1, 2, 3, 4, 5, 6, 7. 2 power 7, okay? So as you can see here, you have 156, okay, is greater than 128. So I will subtract 128 from 156 and I will write 1 here because I have already 1, okay? After that, I will compare the remainder with the other powers. It is the 64, so 22 is lower than 64, so I don't have any 64. Nor I don't have any 32, okay? But 16 I have 1. I can subtract 16, okay? And so on. So the conversion now from a decimal number to its octal equivalent is done by the repeated division method. You simply divide the base 10 number by 8 and extract the remainders. So here are 2 examples to illustrate this method, okay? So you will have 15. I will divide 15 by 8 and I will get the remainder. This is the remainder 7. Okay. I will divide this one, okay, by 8. It will be equal to 0 and this is the remainder. So 15 is equal to 17, okay. 15 in the decimal. It will be equal to 17 in the octal, okay. Convert now to 164. 264 divided by 8, it will be equal to 33, sorry. And as a remainder, I will have 0. So this is the remainder. 33 now divided by 8 is will be equal to 4, and I will have a remainder 1. Okay, and this 4 divided by 8 is equal to 0, and as a remainder I will have 4. So this is my number, 410. Okay. Okay, is it clear? So move now to the last part of this tutorial. It is the interacting with computers interfaces. So the human-computer interactions is the study of how humans interact with computers and their applications. Okay, so the HCI looks at the design of computer systems in which humans and computers need to work together, and tells us how to build user interfaces that are safe, that are efficient, that are easy and enjoyable to use, okay, as well as functional, okay. So HCI is a broad subject covering all aspects of the way in which people interact with computers, and so draws on ideas from many subjects, including computer science, psychology, engineering, artificial intelligence, philosophy, sociology, anthropology, and graphic design. Okay, all these science or this field or these subjects, okay, are okay. We need to have, okay, some ideas about how to interact a human with computers. Okay, so the importance of good user interface design is, okay, a good user interface is one that is easy to use and easy to understand, that meets the needs of the intended users, and that supports users in tasks they wish to undertake. Okay, so this is when we can say that it is a good user interface. A good user interface designer thinks about the users of the user interface and pays great attention to the usability of this interface for users. So a cardinal rule for good user interface design is always to be aware of users' needs, okay? It will respond to the user's need. It will be, okay, as easy as he can or it can, okay, for usability, okay? So user interface design principles. There are several user interface design principles in the HCI literature. So the best known are those applying to visibility, to feedback, to affordance, to simplicity, to structure, to consistency and tolerance of user interface design. Okay, we need to have these, okay, features, okay, for in my user interface. So each design principle has helpful guidelines associated with it, and their application is described by means of examples. Okay, so for the visibility, visibility in the context of user interface design means making it clear what a user interface element is used for. Okay, so all the user interface elements should have good visibility. This can be done by good labeling, okay, like this, print, cancel, okay, and this blue, okay, for this bottom, okay, etc. So in a user interface for DVD player, standard recognizable symbols are used, and buttons have labels to make their purpose clear for users, okay? For the feedback in the context of user interface design means making it clear what action has been achieved through the use of user interface element. So feedback is used to say that one part of an action has finished and another can begin, okay? Feedback can be visual, can be audible, can be tactile, okay? Example, when pressing any key of a mobile phone, a beep is heard. When pressing a button on a user interface, the button is darkened, okay? So this is one feedback, one means of feedback, okay? Ways of feedback. Affordance. Affordance in the context of user interface design means making it clear how a user interface element should be used, okay? It is affordable, okay? So a very simple level to afford means to give a clue of how to interact, okay? So for example, in Windows operating system, buttons are given a shadow which affords pushing. The underlying of links on web pages affords clicking, etc. Okay. Simplicity. Simplicity means keeping things as simple as possible. So to achieve simplicity, employ actions, icons, words, user interface controls that are natural for the user. Use simple language. Break complex tasks into smaller subtasks. Find out what tasks are most common for your users and make these as short as and simple as possible for the user to achieve. Tolerance. Tolerance refers to the ability of a user interface to prevent errors if possible, or to make them easy to recover from if not. So example, to prevent the wrong choice of menu items. Some items may be grayed out, or before deleting a file, a confirm message is displayed. So this is for tolerance usability. Structure now. User interface needs to be structured in a way that is meaningful and useful to users. So it is important to structure the user interface in a way that will be meaningful for the user. Example you have in the Microsoft Word, related comments are grouped together for home here, for insert, okay, for page layout, for references, okay, and in each, okay, group you will have different comments that are related, okay. Consistency in appearance, positioning, and behavior within the user interface makes a system easy to learn and remember. Okay, so example, the icons in the top bar of different Microsoft Office applications are the same and function in a similar way. Okay, all these function okay in a similar way. Okay, thank you for your attention, and feel free to ask question if you have. Okay, if you have any question, you can ask. Thank you very much for your attendance.